Module 7.2, Masking and MP3 Compression. Have you ever had the experience of taking a shower and finding out afterwards that someone had tried to call you on the phone or rung your doorbell and you didn't hear it? Then you've experienced auditory masking. Auditory masking is when the presence of one sound causes a second sound to be softer or inaudible. Masking takes many forms, and we will investigate a few of them. Pure tones that are very close in frequency mask better than tones that are far apart in frequency. When they get very far apart, no masking occurs. Lower frequency tones will mask higher frequency tones better than higher frequency tones will mask lower frequency tones. The louder the tone, the wider the frequency range it will mask. Narrowband sound has the same masking ability as a pure tone. Broadband sounds mask all tones. We will investigate some of these examples of masking in the lab. Here's one example of masking from the auditory demonstration CD. You will hear a familiar clock chiming melody, alternating pure tones with higher frequency complex tones. The melody will play 2 more times, one time with low frequency noise, and the next with high frequency noise. Take notice of the difference. The lower frequency pure tones were masked by the low frequency noise, while the higher frequency complex tones were not. Which of the previously mentioned forms of masking would explain that? The high frequency noise masked the complex tones, but not the pure tones. Why do you think that would be the case? Has this ever happened to you? You start up your car and turn on the radio. You set it for a comfortable volume and start to drive. It's a nice day and you have the windows open. You get onto the highway and realize you can hardly hear the radio, so you turn it up. What has happened here? Has the radio gotten softer? Nope. You've become a victim of partial masking. Partial masking is when a wideband sound causes another sound to appear to be softer than when it's heard alone. Our binaural hearing also has an effect on masking. When listening with 2 ears rather than one, the effects of masking decrease when there is a difference in the sound received by the 2 ears. This is called binaural release from masking, or masking level difference. It turns out that understanding how we hear and how masking affects what we hear has a dramatic effect on the music industry and technology. A little history. Digital audio first started becoming a viable reality in the 1980s. Here's how digital audio works. Think of it this way. There's a worker who measures the amplitude of sound waves. He's very good at what he does and is very fast. He's so fast that he can make 44,100 measurements every second. As quickly as he makes those measurements, he ships that numerical information to a coworker who converts each of those numbers into 16 binary numbers or bits. After he does the conversion, he stores them. Originally, this data was stored on magnetic tape, but now it's generally stored on a hard drive on your computer, smartphone, or in the cloud. In the 1980s, 44,100 numbers times 16 bits added up to a lot of data. About 5 megabytes of data for every minute of recorded audio. And that's for one signal. If we were going to record in stereo, that's 2 audio signals or 10 megabytes a minute. Things were quite a bit different back in the 80s. My very first large hard drive held 20 megabytes of data. It was the size and weight of a large college textbook, and it cost me $1,300. So if it was a good day, I could store a whopping 2 minutes of stereo audio on that $1,300 hard drive. Whoopee! About that time, the internet started to become available to the public, and the music industry saw that this might be a good way to sell music. There was a problem, however. Do you remember dial-up modems? Before the day of fiber optics, DSL, and cable connections, most of the internet worked with dial-up connections. Even with a high-speed modem, it took about an hour to send 10 megabytes of data. So, if you had recorded a 3-minute song in stereo and wanted to send it digitally over the internet to a friend, it would take 3 hours to do that. So the music industry realized that something needed to be done to speed things up. And that's where masking and the Fletcher-Munson curves come into play. Researchers began to realize that there is a lot of sound that we don't hear. Some sounds are too soft to hear, and some sounds are masked. They realized that if they could remove the inaudible material, that they might be able to reduce the amount of data required to store the audio. This would make it possible to store more audio on hard drives and send it over the internet quicker. And so MP3 audio compression was born. It turns out that using MP3 audio compression eliminates 90% of the data needed to store audio. If it's done well, you might not even be able to tell the difference between the MP3 and 44.1 kilohertz 16-bit digital recording. MP3 audio compression is what allows you to have thousands of songs on your portable music device, and with the advent of high-speed internet, the ability to download a 3-minute song in a matter of seconds. Here is the spectrogram which shows the frequency content of a short segment of music. The x-axis is time, and the y-axis is frequency. The top picture is of a full-fidelity recording, while the bottom is the same music with MP3 compression. There is a thin line around 16 kilohertz that was inserted as a marker. What do you notice about the bottom graph? There's no information above 16 kilohertz, and less information between 12 and 16 kilohertz. So, one way of saving data is to eliminate all information in the 16 kilohertz to 20 kilohertz range. Add to that the removal of any audio that is masked, and you've eliminated a lot of data. To review, auditory masking is when the presence of one sound causes a second sound to be softer or inaudible. Pure tones that are close in frequency mask better than tones that are far apart in frequency. Lower frequency tones will mask higher frequency tones better than higher frequency tones will mask lower frequency tones. The louder the tone, the wider the frequency range it will mask. Narrowband sound has the same masking ability as a pure tone. Broadband sound masks all tones. Partial masking is when a wideband sound causes another sound to appear to be softer than when it is heard alone. Binaural release from masking or masking level difference refers to the fact that there is less masking when there is a difference in the sound received by the two ears. MP3 audio compression uses information about masking and how we perceive sound to reduce the amount of data needed to store or transmit a digital audio signal.